Hi. In Gaussian splatting, we represent the world by thousands of these tiny Gaussians. If I make them smaller, you can see each individual one. And each one has a position and opacity and a bunch of other attributes. But one thing that is lacking is information on what object in the scene it belongs to. So, for example, we have no way of telling that the Gaussians of the ground belong to the ground and the ones of this chair belong to this chair. And this is very tricky when we want to do things like editing, because, for example, I might want to just delete this one chair or just delete the background, and that's really hard to do if you just have a bunch of Gaussians in space. So one thing I'm working on is adding semantic information to all these Gaussians. So let me show you a quick demo. So if I turn on instance mode over here, we can see that all the different objects in the scene get a different color. And then I can use this when I'm using my editing features. So for example, I can delete just the background, and just the background is removed, but then all the chairs are still here. Or I can move like one of the chairs up, or delete it, or delete one of these other chairs. Here is an example of a scene that's a lot more complicated. There's a lot of different objects. And then again, if I enable the instance visualization mode, you can see, if we give it a moment, that the different objects in the scene end up getting different colors. And then again, we can do the editing sort of features, like moving things up or deleting things from the scene. So let me talk a little bit about how I did this. So I started off by taking a data set from another paper called panoptic lifting. And in this data set, they were solving a similar problem, but for a neural radiance field. So it wasn't, their method wasn't directly applicable to what I was working on. But their data set was very helpful, because what they did was they took this, these images of this scene, and they used segment anything from Meta to do instant segmentation on all the images. And then they did some extra post-processing to make sure that the instances are consistent between images. So then I took that data set and I trained my custom Gaussian splatting model based on that. And what I did was I assigned a bunch of extra numbers to every single Gaussian that represent the probability of a Gaussian belonging to a specific instance. So for example, for training this scene, there's 5 different instances. There's the 4 couches, and then there's the background. So when training this scene, I assigned 5, I have 5 extra numbers appended to every single Gaussian, and each one represents the probability of that Gaussian belonging to that instance. So for example, belonging to this chair, or this chair, or this chair. And then as I'm training, just like I can sort of splat those Gaussians onto the screen to create the RGB photo and get a loss from that to compare it to the ground truth, I can also just render a photo of just those instance numbers. So for example, if I just look at the first instance number, all of the places that are white represents the Gaussians that cause those pixels to be lit have a high instance number for the background probability. While for these other ones, this is, for example, that number assigned to the first couch. You can see all of the Gaussians near that first couch have that high, are white, meaning they have a high probability of belonging to that first couch. And similarly for all the other couches. And then what I can do is I can use this image and compare this to my original instance images to sort of get a loss and then optimize those instance numbers. So, and then how it works in the viewer is that when I export, I don't have to export all of those 5 numbers. I can just rely on just having one float. And so this is kind of the input to my viewer. You can see that there's just one extra float on the Gaussian splat file, and that's the instance number. And this is better because because this is on the web. We don't want to be sending those giant files over. One thing that's bad about the way I'm doing it during training is that because I'm assigning a lot of different numbers to every Gaussian, if the scene has a lot of different instances, then I run into memory limitations. The originally I tried training with just having one extra number assigned to each Gaussian and just using that one number sort of to represent the instances. But the problem with that was I think that the space was just like too low dimensional. So the instance numbers weren't correctly like separated. It was kind of like the Gaussians were like interpolating between the two different couches. So when I added one separate number for every Gaussian, it worked much better. Like you can see, it does a pretty good job. But I recently talked to someone and they gave me a really good idea, which is to, instead of having one number, which doesn't work, of course, or having one number for every instance, just have like four or three or four numbers, and then you have this, and then somehow embed those instance numbers in that space. And then when you do that, you should still have a lot of room in that space for separating the instance numbers, but you don't have that like unlimited memory usage if the scene has like 100 instances or something. So that's something I'm gonna try next. But right now it's just using one instance number, one extra number for every instance of the scene. Yeah. So this viewer, it's an open source viewer. I didn't build the viewer from scratch, but I added all of the editing features and all of the semantic features to it. So the viewer originally was just viewing the splats, but I added a whole bunch of new features. So yeah, thanks for watching.